Visually impaired audio video. Chapter Chemical Kinetics. Introduction. During the study of various reactions which may be carried out in the laboratory or industry or may be occurring in the life processes or any other applied field, we are interested to know how fast the reaction occur, the rate of the reaction. We are further interested to know how the reaction occur, the step in which the reaction occur called the mechanism of the reaction. Also, we are interested to know how the rate of reaction is affected by changing the concentration of the reactant or temperature or adding a catalyst, etc. The branch of physical chemistry which deal with the study of the rate of the reaction, the factor which govern these rates and the mechanism by which the reaction proceed is called chemical kinetics. Further, a chemist is not interested in the kinetic study of all reactions. For this purpose, the various reactions are divided into three categories. Those reactions which take place almost instantaneously, many ionic reactions like AgNO3 plus NaCl give rise to AgCl plus NaNO3. BaCl2 plus H2SO4 give rise to BaSO4 plus 2HCl. Second, those reactions which take place extremely slowly, for example, rusting of iron, combination of hydrogen and oxygen at ordinary temperature, etc., are such reactions which take months or even years before any detectable change occur. Third, those reactions which take place at measurable speeds. Between two extreme discussed there are a large number of reactions which take place at speed which can be conveniently measured. A few examples including in this category are ethyl acetate plus H2O give rise to acetic acid plus ethyl alcohol. Cane sugar plus H2O give rise to glucose plus fructose. Ammonium nitrate when heat give rise to 2H2O plus N2. Hydrogen peroxide give rise to H2O plus O2. Another question that immediately arises in our mind is why the speed of different reactions are different. An obvious reason is that a reaction involves the breaking and making of bonds. Since different bonds require different amount of energy for breaking and different amount of energies are evolved when different kind of new bond are formed, the rate of different reaction are different. The instantaneous nature of the ionic reaction is due to the fact that these do not involve any breaking of bond, as ions are already present in the aqueous solution. Lastly, it may be mentioned that all chemical reactions do not proceed in a simple way. Complications are caused in the study of the rate of reaction when the reaction is reversible or some side reaction take place simultaneously. In the present chapter, we shall take up the different aspects concerning the kinetic of reaction. Rate of reaction. The rate of reaction may be defined as the speed or the velocity with which the reaction takes place, or the rate of a reaction may be defined as the change in the concentration of any one of the reactant or product per unit time. For example, consider the dissociation of PCl5 to give PCl3 and Cl2. Rate of this reaction is equal to decrease in the concentration of PCl5 upon time taken, or increase in the concentration of PCl3 or Cl2 upon time taken. Units of rate of reaction. Since the concentration is usually expressed in moles per liter and the time is taken in second or minute, the unit of the rate of reaction are therefore mole liter inverse second inverse or mole liter inverse minute inverse or atmosphere second inverse, etc. for gaseous reactant and product. However, a difficulty arises in stating the rate of reaction as above. This is because, according to the law of mass action, the rate of a reaction depends upon the molar concentration of the reactant, and the concentration of the reactant keep on decreasing with the passage of time. while that of product keeps on increasing. Therefore, the rate of reaction does not remain constant throughout. Thus, we should take the rate of a reaction only at a particular instant of time. Hence, the rate of reaction is defined as follows. The rate of a reaction at any time is defined as the change in the concentration of any one of the reactant or product per unit time at that particular instant of time, expressing the rate of a reaction. Since the rate of a reaction is changing continuously throughout the course of the reaction, therefore, to state the rate of reaction at any instant of time, a small interval of time dt may be taken during the rate of reaction may be assumed to be almost constant. Suppose dx is the small change in concentration of any one of the reactant or product during the small interval of time dl dt, then the rate of reaction may be expressed as rate of reaction is equal to dx upon dt. Further, if the rate is expressed in term of one of the reactant, a negative sign is attached to show that the concentration is decreasing. If the rate is expressed in term of any product, a positive sign is used to show that the concentration is increasing. For example, consider the reaction A plus B give rise to P plus Q. The small change in concentration dC corresponding to small interval of time dt may be noted directly from the graph. Then assuming that the rate remain constant during this small interval of time, the rate may be calculated as dC upon dt. If concentration of one of the product is studied at different instant of time and the values are plotted against the corresponding time, a graph of the type shown in figure 5.61c is obtained. The rate of reaction at any time is obtained by finding the slope of the tangent to the curve at the point corresponding to that time. Factors influencing the rate of reaction. The rate of reaction depends upon a number of factors. A few important out of these are as follows. First, nature of the reactant, concentration of the reactant, temperature of the system, presence of a catalyst, nature of solvent, presence of radiation. Each of these factors below one by one. Nature of the reactant. To understand how the nature of reactant play an important role in influencing the rate of a reaction, let us consider the following two examples. Oxidation of ferrous ion and oxalate ion by acidified KMnO4 solution. Both reactions are similar as represented below. At the same temperature, the first reaction is very fast, whereas the second reaction is quite slow as indicated by the rate of disappearance of pink color of KMnO4. In fact, in the titration, the second reaction is so slow that heat is required. Thus, in the above case, even if the concentration of similar reactant are taken to be same in the two reactions and the temperature is also kept the same, the rate of these two reactions are still different. This is obviously only due to the difference in the nature of the reducing agent, Fe2 positive ion and C2O42 negative ion. Oxidation of nitric oxide and carbon monoxide by air. These reactions may be represented as. Thus, the above two equations are exactly identical in the balanced form, but still at the same temperature, the first reaction is fast, whereas the second is slow. Again, in this case, also, clearly the difference in the reaction rate must be due to the difference in the properties of NO and CO. As mentioned in section 5.1, the difference in the rate may be attributed to the fact that a reaction involves breaking of the bond of the reacting molecule and the formation of new bond in the product molecule. Energy is required for the breaking of bond and energy is released when a bond is formed. The net energies involved are different for different reactions and hence the rate are different. Second, concentration of the reactant. As a reaction proceeds, the reactant are consumed. Therefore, the concentration of the reactant decreases with the passage of time. It is observed experimentally that the rate of reaction also decreases as the time passes. This clearly indicates that the rate of reaction is directly related to the concentration of the reactant. The variation of the concentration of a reactant and hence that of the rate of reaction with time may be represented graphically. Then the rate of reaction depend upon the concentration of the reacting species is further confirmed from the simple example of rusting of iron. Rusting of iron is faster in the rainy season when the concentration of water vapor in the air is higher than in the dry weather. The effect of concentration is explained on the basis of collision theory of reaction rate. The rate of reaction depends upon the number of collision between the molecule. Higher the concentration, greater is the number of collision. Third, temperature of the system. Temperature has a very significant effect on the rate of a reaction. So much so that a rise in temperature not only increase the speed of the reaction, but in many cases it actually initiates the reaction. Thus, to study the effect of temperature on the reaction rate, two types of cases are observed. For most of the reaction, maybe exothermic or endothermic, the rate of reaction increase with rise of temperature. As the rough rule, in general the rate of reaction become nearly double or sometimes even triple for every 10-degree rise of temperature. This is generally expressed in the form of temperature coefficient, as temperature coefficient is equal to Kt plus 10 upon Kt is equal to 2, where Kt and Kt plus 10 are the specific reaction rate at T degree Celsius and T plus 100 T plus 10 degree Celsius respectively. To cite simple example, the temperature coefficient for the dissociation of gaseous hydrogen iodide, but for the combination of methyl iodide and sodium ethoxide in solution, the value is about 2.9. It is really a fantastic observation because the number of collision increase only by about 2% for 10-degree rise at ordinary temperature, whereas the reaction velocity may increase by 100 to 200% or even more. A large number of reactions are known which do not take place at room temperature but occur readily at higher temperature. Reaction between hydrogen and oxygen to form water take place only when an electric spark is passed. Similarly, it is well known that coal can be kept in oxygen for years without burning, but once the ignition is initiated, it goes on till the whole of coal burn away. The above observations are explained on the basis of collision theory. According to this theory, substances react because their molecules collide with each other. All collision are however not effective collision. An effective collision is that collision which results into a chemical reaction. In order that a collision may be effective, the colliding molecule must possess a certain minimum amount of energy called threshold energy. This threshold energy may be defined as the minimum amount of energy which the colliding molecule must possess in order that the collision between them may be an effective collision. The concept of effective collision and threshold energy is just like the fact that some damage occurs to the two colliding cars only if they have a certain minimum speed. If they collide with a speed less than this speed, no damage may occur to the cars. The two types of cases may now be easily explained as follows. Explanation for the increase in reaction rate with rise to temperature. The different molecules of the reactant do not possess the same energy. If the energies of the reactant molecule are plotted against the corresponding fraction at a particular temperature T, a curve of the type shown in figure 5.3a is obtained. In the figure, ET represents the threshold energy. The shaded area represents the fraction of molecule with energies equal to or greater than the threshold energy. As the temperature is increased from T to T plus 10 degrees Celsius, the curve shifts as shown. The shaded area beyond ET now become almost double. This shows that the fraction of molecule possessing energy equal to or greater than the threshold energy become almost double, as the rate of reaction also become almost double. Explanation of the non-occurrence of reaction at room temperature and occurrence at higher temperature. At room temperature, there are no molecule possessing energy greater than the threshold energy, so there is no reaction. When temperature is increased, the molecule of the reactant absorb heat energy, and thus a number of molecules start attaining energy equal to or greater than the threshold energy, and hence the reaction starts. The extra amount of energy which the molecule of the reactant have to observe so that their energy become equal to the threshold energy is called the activation energy. In other words, activation energy is equal to threshold energy minus energy actually possessed by the reacting molecule. Thus, in order that the reactant may change over to product, they have to absorb some energy and thus cross a barrier called activation energy barrier. Presence of catalyst. A catalyst is substance which increases the speed of a reaction without itself undergoing any chemical change. For example, the decomposition of KClO3 is greatly accelerated by the addition of small amount of MnO2, which itself does not undergo any chemical change during the reaction. The presence of a catalyst provides an alternate path with lower energy barrier. Thus, activation energy is lowered and hence a greater number of molecules can cross the barrier and change over to product. The following two addition results may be derived. Delta E for the catalyzed reaction is the same as delta E for the uncatalyzed reaction. For reversible reaction, the activation energy for the reverse reaction is lower to the same extent as for the direct reaction, as the presence of catalyst of such reaction increase the speed of the forward reaction and that of the backward reaction to the same extent. Consequently, the equilibrium is attained quickly, but it otherwise not disturbed. Nature of the solvent. In terms of dielectric constant of the solvent, in case of ionic reaction taking place in solution, for the given ion at a particular temperature, the rate constant K of that ionic reaction is found to vary with the dielectric constant of the solvent according to the equation, where A and B are the constant for the given pair of ion. Thus, a plot of is a straight line. The equation 1 shows that in that anti-logarithm K varies inversely with the dielectric constant of the solvent. In terms of polarity of the solvent, the polarity of the solvent affects the rate of reaction according to the following general rule. A polar solvent is expected to accelerate a process in which polar substance is a product and retard the process in which the product formed is nonpolar. For example, in the reaction between triethylamine and ethyl iodide, the product is a salt and hence more polar than the reactant. The rate of reaction would increase as the polarity of the solvent increase. On the other hand, in the acetylation of alcohol, the products are less polar than the reactant. Therefore, the effect of solvent is reverse of that in the first case. In the decomposition of nitrogen pentoxide, the difference in the polarity between the reactant and the product of the rate determining step is so small that the rate is almost independent of the nature of the solvent. In terms of interaction of the reactant or activated complex with the solvent, it is found that the solvent affects the rate of reaction significantly due to the interaction of the reactant or the activated complex with the solvent. The effect of this interaction is to lower the potential energy of the substance by an amount equal to the energy of solvation. If both or if one or both the reactant are solvated, but the activated complex is not, the decrease in the potential energy of the former means that the required activation energy for the reaction is increased. The rate of reaction will therefore decrease. If the activated complex is solvated but the reactant are not, the potential energy of the activated complex will decrease, which means lowering of the required activation energy and hence increase in the rate of reaction. In case the reactant as well as activated complex are solvated, the potential energy of both will decrease. The effect on the overall activated energy and as the rate of reaction will be small. For this reason, the reaction between triethylamine and ethyl iodide in nitrobenzene has exceptionally high rate. Presence of radiation. Some reactions which do not take place under ordinary conditions take place in the presence of light. The reaction between H2 and Cl2 to form HCl. Such reactions are called photochemical reaction. The reason is that the radiation gives energy which is absorbed by the reactant molecule and thus the energy barrier is easily crossed. Order of a reaction and specific rate constant. Specific reaction rate. In order to understand what we mean by the order of reaction, consider the general reaction. Experimentally, it is observed that the rate of this reaction may not depend upon all the A concentration term of A and all the B concentration term of B. Suppose experimentally the rate of reaction is found to depend upon alpha concentration term of A and beta concentration term of B. Then we may write rate is directly proportional to A raised to the power alpha dot B raised to the power beta, or rate is equal to K A raised to the power alpha B raised to the power beta, where A and B are the molar concentration of A and B respectively, and K is a constant called velocity constant or rate constant. If all concentrations are taken as unity, then the rate constant may be defined as the rate of the reaction when the concentration of each reactant is taken as unity. That is why the rate constant is also called specific reaction rate. Equation 1 is called the rate law. It differs from the law of mass action in the fact that whereas the rate law states that the rate of reaction depends upon the concentration term on which the rate of reaction actually depends, as observed experimentally. The law of mass action is simply based upon the stoichiometry of the equation. For example, in the above case, according to rate law, rate is equal to A raised to the power alpha, B raised to the power beta. According to law of mass action, rate is equal to K A raised to the power alpha, B raised to the power beta. The sum of the concentration term on which the rate of reaction actually depends, as observed experimentally, is called the order of the reaction. Thus, in the above case, order of reaction is equal to alpha plus beta. Hence, the order of reaction may also be defined as the sum of exponent to which the concentration term in the rate law are raised to express the observed rate of reaction, depending upon whether alpha plus beta is equal to 0, 1, 2, or 3. The reactions are said to be of zero order, first order, second order, and third order respectively. Alpha and beta are called the order of reaction with respect to A and B respectively. For better understanding, a few examples are given below. Experimentally, it is found that rate of reaction is directly proportional to N2O5. It depends only on one concentration term, as the reaction is said to be of first order. Further, it may be mentioned here that the order of reaction may not be always a whole number. For example, acetaldehyde decompose as. Experimentally, it is found that order of reaction is equal to 1.5. Units of rate constant for reaction at different order. For a reaction of nth order, rate is equal to concentration raised to the power n. For zero order, unit of rate constant is equal to mole liter inverse second inverse. For first order reaction, unit of rate constant is equal to second inverse. For second order reaction, unit of rate constant is equal to liter mole inverse second inverse. For third order reaction, units of rate constant is equal to liter square mole square inverse second inverse. These units will also be derived from the expression for rate constant for reactions of different order discussed in the following section. Reactions of the zero order. A reaction is said to be of zero order if the rate of reaction is independent of the concentration of all reactant. Obviously, for such reaction, the rate of reaction remain uniform throughout. There are two types of reaction which has been found to be of zero order. Photochemical reaction. Photochemical reaction are those reactions which take place in the presence of light. Many such reactions have been found to be of zero order. For example, the combination between hydrogen and chlorine in presence of light may be studied by enclosing these gases in a tube and inverting the tube in a trough of water. When the reaction takes place between H2 and Cl2, HCl is formed which dissolve into water and the level of water in the tube rises. Thus, through the quantities of H2 and Cl2 decrease, their amount per unit volume remain the same. The concentration of H2 and Cl2 remain constant. Heterogeneous reaction. A heterogeneous reaction means a reaction in which the reactant, product, and the catalyst are present in different phases. Some of these reactions have been found to be of zero order. Two well-known examples of these type are the decomposition of hydrogen iodide on the surface of gold and the decomposition of ammonia on the surface of tungsten, molybdenum, or platinum at high temperature. The gaseous molecule of the reacting substance get absorbed on the surface of the catalyst. The surface is thus fully occupied with the molecule of the reactant. Some of these molecules react to form the product, but immediately new molecules take up their position, and thus the concentration of the reacting molecule remain constant on the surface and as the rate of reaction remain constant irrespective of the total amount of the gaseous reactant taken initially. Expression for the rate constant for a reaction of zero order. For a reaction of zero order, rate is equal to dA upon dt is equal to k a raised to the power 0 is equal to k. By integrating both sides, we get the value of I. Now if we substitute this value of I in equation 2, we get rate constant. Alternatively, for a reaction of zero order, k dx is equal to k dt. Integrating both sides, we get x plus kt plus I. When t is equal to 0, the amount reacted x is equal to 0, I is equal to 0. Substituting in the above reaction, we get x is equal to minus kt. The amount reacted is directly proportional to time. Characteristics of reaction of zero order. Any reaction of zero order must obey equation 5, 6 or 7. And equation 5 is of the type y is equal to mx plus c. The equation of a straight line. Plot of A versus T will be a straight line with intercept A naught on the concentration axis and a negative slope. Also from equation, as rate is equal to k a raised to the power 0 is equal to k. A plot of rate versus concentration will be a line parallel to the concentration axis. Half-life period. The time in which half of the initial amount react. When T is equal to T half, A is equal to A naught half. Substituting in equation 7, we get T half is equal to A naught upon 2K. Thus, half-life period of a zero-order reaction is directly proportional to initial concentration. If initial concentration is doubled, the time taken for half of the reaction to complete is also doubled, and so on. Units of rate constant K. Mole liter inverse time inverse. Reaction of the first order. A reaction is said to be of the first order if the rate of the reaction depends upon one concentration term only. Thus, we may have for the reaction A give rise to product. Rate of reaction is directly proportional to concentration of A. For the reaction 2A give rise to product, rate of reaction is directly proportional to A only. For the reaction A plus B give rise to product, rate of reaction is directly proportional to A or B only. Let us consider the simplest case, A give rise to product. Suppose we start with A moles per liter of the reactant A. After time t, suppose x mole per liter of it have decomposed, reacted. Therefore, the concentration of A after time t is equal to A minus x moles per liter. Then according to law of mass action, rate of reaction is directly proportional to A minus x. dx upon dt directly proportional to A minus x, or dt by dx by dt is equal to k A minus x, where k is called the rate constant or the specific reaction rate for the reaction of the first order. The expression for the rate constant k may be derived as follows. Equation 1 may be written in the form dx upon A minus x is equal to k dt. Integrating equation 2, we get minus antilogarithm A minus x is equal to kt plus I, where I is a constant of integration. In the beginning, when t is equal to 0, x is equal to 0, as no substance has reacted at the start of the reaction. Putting these values in equation 3, we get minus antilogarithm of A is equal to I. Substituting this value of I in equation 3, we get k is equal to 1 upon t antilogarithm A upon A minus x. or k is equal to 2.303 upon t logarithm of a upon a minus x. Equation 6 is sometime written in another form, which is obtained as follow. If the initial concentration is C0 and the concentration after time t is Ct, then putting A is equal to C0 and A minus x is equal to Ct, equation 6 becomes k is equal to 2.303 upon t logarithm C0 upon Ct. Equation 5 can be written in the form Kt is equal to nt logarithm A upon A minus x. Putting A is equal to C0 and A minus x is equal to Ct, we get Kt is equal to anti-logarithm C0 upon Ct. This equation can be written in the exponential form as Ct is equal to C0 e raised to the power minus Kt. Some important characteristics of first order reaction. Any reaction of the first order must obey equation 6 or 7 or 10. This may be tested in any one of the following ways. Substitution method. Starting with a known concentration A, the concentration of the reactant A minus X or Ct at different interval of time may be noted. For every value of t, the corresponding value of A minus X, Ct may be substituted in equation 6 or 7. If the value of K thus obtained are nearly constant, the reaction of first order. Graphical method. Equation 7 may be written as this is the equation of a straight line. Thus, if log Ct or log A minus X value are plotted against time t, the graph obtained should be a straight line with a negative slope if the reaction is of the first order. The intercept made on the y-axis would be log C0 and the slope of the line would be minus k upon 2.303. From this, the value of k can be calculated. If the initial concentration is not known with certainty, then to test a first order reaction, an equation is obtained in which the initial concentration A is eliminated. This is done as follows. Suppose after time t1, the concentration is A minus x1 and after time t2, the concentration is A minus x2. Then according to equation 6, k is equal to 2.303 upon t1 logarithm of A upon A minus x1. K is equal to 2.303 upon t2 logarithm A upon A minus x2. Equation 12 and 13 may be written as subtracting equation 14 from equation 15 we get where Ct1 and Ct2 are the concentration after time T1 and T2 respectively. That the reaction is of the first order may be tested either by substitution method or by graphical method. If k is equal to 2.303 upon T2 minus T1 logarithm A minus x1 upon A minus x2 is equal to 2.303 upon T2 minus T1 logarithm Ct1 upon Ct2, where Ct1 and Ct2 are the concentration after time T1 and T2 respectively. The time taken for any fraction of the reaction to be completed is independent of the initial concentration. For example, let us test the truth of this statement for half of the reaction to be completed. Equation 5 may be written as T is equal to 2.303 upon K logarithm A upon A minus X. When half of the reaction is completed, X is equal to A by 2, representing the time taken for half of the reaction to be completed by T half. Equation 17 becomes T half is equal to 0.693 upon K. Thus A does not appear in this equation, so that T half is independent of A. Similarly, it can be seen that T half, T2 by 3 etc. will also be independent of the initial concentration. The time taken for half of the reaction to be completed, the time in which the concentration of a reactant is reduced to half of its original value, is called half-life period of the reaction. The above result can also be used as a test a reaction of first order. This method is called fractional life method. The unit of K are independent of the unit. The units of K are independent of the unit in which the concentration are expressed. This is obvious from equation 6 because in this equation K depends upon the ratio of two concentration A upon A minus X and the time t. Thus, so long as both A and A minus X are expressed in the same concentration units, the value of K is not affected. The units of K therefore depend only upon the units of time t. Depending upon whether t is expressed in second or minute or hour, K would be in second inverse or minute inverse or hour inverse respectively. Examples of the reaction of first order. Broadly speaking, the reaction of the first order may be divided into two categories. Reaction taking place in the gaseous phase, reaction taking place in solution. For simplicity, the various examples of the reaction of the first order may be further classified into three types as described below. Reaction involving decomposition of a substance. These are the most common example of the reaction of the first order. The decomposition of a substance may take place in the gaseous phase or in solution, the latter being more common. A few examples of this type are briefly explained below. Decomposition of nitrogen pentoxide. This was the first reaction studied in the homogeneous gas phase and found to be of first order. The compound nitrogen pentoxide is a volatile solid which decomposes in the gaseous state as well as in the form of its solution in an inert solvent like carbon tetrachloride, chloroform, etc. according to the equation. When the reaction is carried out in the solution, N2O4 and NO2 remain in the solution and the volume of oxygen gas collected is noted at different interval of time. It is obvious that volume of oxygen gas collected at any time directly proportional to amount of N2O5 decomposed. Volume of oxygen gas collected an infinite time directly proportional to amount of N2O5 initially taken. Substituting these values in the first order equation, K is equal to 2.303 upon T logarithm V infinity upon V infinity minus Vt. Pseudo-unimolecular reaction. Consider the following acid catalyzed reaction: hydrolysis of ethyl acetate, inversion of cane sugar. Both the above reactions are bimolecular but are found to be of first order, as experimentally it is observed that for the first reaction, rate of reaction directly proportional to ethyl acetate only, and for the first reaction, rate of reaction directly proportional to sucrose only. The reason for such a behavior is obvious from the fact that water is present in such a large excess that its concentration remain almost constant during the reaction. Such a reaction which are not truly of first order but under certain conditions become reaction first order. are called pseudo-unimolecular reaction. The kinetics of the above reaction have been studied as follows. In this reaction, acetic acid is one of the product the amount of which can be found by titration against standard NaOH solution. But being an acid catalyzed reaction, the acid present originally as a catalyst also react with NaOH solution. Hence, a little careful thought revealed that for the same volume of reaction mixture withdrawn at different time, volume of NaOH solution used in the beginning at zero time directly proportional to amount of acid present only as catalyst. Volume of NaOH solution used at any instant of time directly proportional to amount of acid present as catalyst plus amount of CH3COOH produced. Combining result 1 and 2 we get X is directly proportional to Vt minus V naught. Combining result 1 and 5 we find that A is directly proportional to V infinity minus V naught. From equation 4 and 6 we get A minus X directly proportional to V infinity minus Vt. Substituting the value of A and A minus X from equation 6 and 7 in the first order equation we get K is equal to 2.303 upon T logarithm V infinity minus V naught upon V infinity minus Vt. Reaction of the second order. A reaction is said to be of second order if the rate of reaction depend upon two concentration terms. Two types of reaction are possible. Reaction involving only one reagent, one reactant of the type 2A give rise to product for which the rate of reaction directly proportional to A raised to A square. Reaction involving two different reactant of the type A plus B give rise to product for which the rate of reaction directly proportional to AB. The constant K in the above equation is called the rate constant for reaction of the second order. For reaction involving only one reactant, the general equation for such reaction is 2A give rise to product. Suppose the initial concentration of A is equal to A moles per liter. Decrease in the concentration of A at any instant of time is equal to X moles per liter. Concentration of A at the instant of time T is equal to A minus X moles per liter. Applying the law of mass action, the rate of reaction will be given by dx by dt is directly proportional to A square. Dx upon dt is equal to K A minus X whole square, where K, as already mentioned, is the rate constant for the second order reaction. Equation 1 may be written as dx upon A minus X whole square is equal to K dt. Integrating this equation we get A 1 upon A minus X is equal to Kt plus I, where I is constant of integration in the beginning at time t is equal to 0, x is equal to 0. Putting these values in equation 2 we get 1 upon A is equal to I. Substituting this value of I in equation 2 we get K is equal to 1 upon T x upon A minus X. If the initial concentration is written as C naught and the concentration at any instant of time t as Cp, then A is equal to C naught and A minus X is equal to Ct. Substituting these result in equation 3 we get K is equal to 1 upon T 1 upon Ct minus 1 upon C naught. This is another form of the expression of the rate constant of second order reaction. For reaction involving two different reactants, the general equation for such a reaction can be written as A plus B give rise to product. If the initial concentration of A and B are same and each is equal to A moles per liter, then the method of derivation and the ultimate expression would be same as in the above case. However, if the initial concentration of A and B are different, then the expression for the rate constant is derived as follows. Suppose the initial concentration of A is equal to A moles per liter. The initial concentration of B is equal to B moles per liter. Amount of A that react in time t is equal to X moles per liter. Then the amount of B that would react in the same time would also be is equal to X moles per liter. At any instant of time, concentration of A is equal to A minus X moles per liter. Concentration of B is equal to B minus X moles per liter. Applying the law of mass action, we get dx by dt is equal to K A minus X into B minus X, where as before K is the rate constant. Equation 6 may be written as dx upon A minus X into B minus X is equal to K dt. Resolving the left hand side into partial fraction, equation 7 may be written as integrating this equation we get 1 upon A minus B into anti-logarithm A minus X upon B minus X is equal to KT plus I, where I is the constant of integration. But at t is equal to 0, x is equal to 0. Putting these values in equation 8, we get 1 upon A minus B anti-logarithm of A upon B is equal to I. Putting this value in equation 8, we get K is equal to 2.303 upon T A minus B logarithm of B A minus X upon A B minus X. Equation 10 then become K is equal to 2.303 upon T C naught of A minus C naught of B logarithm C naught B CTA upon CBA CTB. An interesting result follow from equation 10. If one of the reactant is present in excess, say B is in excess, B will be very large in comparison to A, so that A minus B is equal to minus B and B minus X is equal to B. The equation 10 becomes K is equal to 2.303 upon BT logarithm of A upon A minus X. Some important characteristics of second order reaction. Any reaction of the second order must obey any one of the equation out of 4, 5, 10 and 6. This may be tested either by substitution method or by graphical method. In the former method, the appropriate value of A, B and X are substituted for the corresponding time t, and the constancy in the value of K proves the reaction to be second order. In the latter method, if equation 5 is used, it may be written as Kt is equal to 1 upon Ct minus 1 upon C naught. This equation is like y is equal to mx plus c, the equation of a straight line. Hence, a plot of 1 upon Ct versus t should be a straight line if the reaction is of second order. The slope of the line will directly give the value of K. This equation is again like y is equal to mx plus c, and as the plot of logarithm Ct of A upon Ct of B versus t should be a straight line. If the reaction is of the first second order, the time taken for any fraction of the reaction to be completed is inversely proportional to the initial concentration. As an example, let us calculate the time taken for half of the reaction to be completed. If time taken for half of the reaction to be completed is represented by T half, then X is equal to A upon 2, T is equal to T half. Put this value in equation 4, we get T half is inversely proportional to A. Similarly, it can be seen that for any fraction of the reaction to be completed, the time taken is inversely proportional to A. The units of the rate constant K depend not only upon the unit of time but also upon the unit in which the concentration are expressed. This is obvious from the equation 4, 5, 6 or 11 because there is one extra concentration term in the denominator in each of these equations. For example, using equation 4, the dimensions of K may be calculated as follows. Thus, if concentration is expressed in moles per liter and time in minutes, the unit of K will be mole per liter inverse, minute inverse, liter mole inverse, minute inverse. If the time is in second, the unit of K will be liter mole inverse, second inverse. Examples of the reaction of second order. Reaction takes place in the gaseous phase. Homogeneous gaseous reaction of the second order are very common. In this category are included mostly the thermal dissociation reaction, like thermal dissociation of acetaldehyde, ozone, nitrogen dioxide, chlorine monoxide, etc. Reaction taking place in solution. A few examples of this category include saponification of ester, reaction of alkyl halide with tertiary amine, conversion of ammonium cyanate into urea, etc. As an example of the gaseous reaction, the thermal decomposition of acetaldehyde, and as an example of the reaction in solution, saponification of ester may be discussed as follows. Thermal decomposition of acetaldehyde. The thermal decomposition of acetaldehyde vapor takes place according to the equation. From this reaction, the reaction appears to be of the first order, but experimentally it is found to be of second order and hence is preferably written as the reactant and the product are all gases. The progress of the reaction is followed by simply noting the pressure of the reaction mixture at different interval of time. Further, as one molecule of acetaldehyde on decomposition produces 2 moles, pressure increase as the reaction progresses. Reaction of the third order. A reaction is said to be of third order if the rate of reaction depends upon 3 concentration terms. The following 3 types of reaction are possible. Reaction involving 3 molecules of different substance. A plus B plus C give rise to product. Reaction involving 2 molecules of one substance and 1 molecule of another substance. 2A plus B give rise to product. Reaction involving all the 3 molecules of the same type. 3A give rise to product. The simplest case is the reaction of the last type. The expression for the rate constant of such a reaction may be derived as: suppose A is the initial concentration of A and X is the decrease in concentration of A in time t. Then the concentration of A after time t is equal to A minus x. Now, according to the law of mass action, the rate of the above reaction at any instant of time t will be given by dx upon dt directly proportional to a raised to the power 3. Dx upon dt is equal to k e minus x raised to the power 3, where k is the rate constant for the third order reaction. Equation 1 may be written as dx upon a minus x whole cube is equal to k dx k dt. Integrating this equation, we get 1 upon 2 into a minus x whole square is equal to kt plus I, where I is the constant of integration. Now at t is equal to 0, x is equal to 0. Putting this value in equation 2, we get 1 upon 2a square is equal to I. Substituting this value in equation 2, we get k is equal to 1 upon 2t. K is equal to 1 upon 2t into x into 2a minus x upon a square into a minus x whole square. Some important characteristics of third order reaction. Any reaction third order of the type 3a give rise to product and 2a plus b give rise to product if the initial concentration of A is equal to B is equal to C is equal to A must obey equation 4 and 5. This may be tested by the substitution method or by the graphical method as usual. The time taken for any fraction of the reaction to be completed is inversely proportional to the square of the initial concentration. For example, the time taken for half of the reaction to be completed may be calculated as follow. When x is equal to a by 2, t is equal to t half. Putting this value in equation 4, we get t half is equal to 3 upon 2k a square. T half directly proportional to 1 by a square. Similarly, it can be seen that for any fraction of the reaction to be completed, t is inversely proportional to a square. The units of the rate constant k depend upon the unit of time and that of the concentration. This may be seen by calculating the dimensions of k with the help of equation 4 as follow. The same result follow directly from equation 5. Thus, if concentration is expressed in moles per liter and time in minutes, the unit of k will be mole per liter square inverse minute inverse, and if time is expressed in seconds, the unit of k will be liter square mole square inverse second inverse. Examples of the reaction of third order. Reaction taking place in the gaseous phase. Only 5 homogeneous gas reactions of the third order are known so far. Each of these involve nitric oxide as one of the reactant and the second reactant being either chlorine, bromine, oxygen, hydrogen or deuterium. The reaction may be represented as follow. Reaction taking place in solution. Very few examples of the reaction of the third order taking place in solution are known. Even the order of some of these reactions is doubtful. As an example, let us consider the reduction of ferric chloride by stannous chloride. The kinetics of this reaction is studied by mixing aqueous solution containing equivalent amounts of FeCl3 and SnCl2 and then withdrawing definite amount of the reaction mixture at regular interval of time, running it into mercury chloride solution to remove the excess of SnCl2 and titrating the solution against the standard potassium dichromate solution to find the amount of ferrous ion present. The reaction, though reported to be of the third order earlier, is found to be of the second order according to recent investigations. Reaction of higher order cause of their being rare. It is observed that whereas reactions of first order are large in number, the reactions of second order are less in number. The reaction of third order are still less, and the reaction of fourth order are very rare. The reason for such an observation may be explained on the basis of collision theory. According to this theory, in order that a reaction may take place between certain molecules, these reactions must come together simultaneously to collide with each other. As the probability of two molecules, therefore, the reaction of third order are fewer than those of second order. Similarly, the chance for four or more molecules to come together simultaneously and collide are still less. Hence, the reaction of fourth or higher order are very rare. Half life period. It has been stated in the preceding section that the time taken for half of the reaction to be completed, the time in which the concentration of a reactant is reduced to half of its original value, is called half-life period of reaction. The conclusion drawn about the half-life period for the reaction of different order may be summarized as follows. For reaction of zero order, T half is directly proportional to A. Half-life period is directly proportional to the initial concentration. For reaction of first order, K is equal to 0.693 upon K. Half-life period is independent of the initial concentration. For reaction of second order, half-life period is inversely proportional to the initial concentration. For reaction of third order, half-life is inversely proportional to the square of initial concentration. For general For a reaction of nth order, T half is inversely proportional to A raised to the power n minus A. 1. Molecularity of a reaction. According to the collision theory, in order that a reaction may take place, the molecule must come closer together and collide with each other. The number of atom, ion or molecule that must collide with each other simultaneously so as to result into a chemical reaction is called the molecularity of the reaction. In case of simple reaction, the molecularity is simply the sum of the molecule of the different reactant as represented by the balanced chemical equation. A few examples are given below. Decomposition of F2O2, the balanced equation is, hence the molecularity of the reaction is 1 and the reaction is called unimolecular. Dissociation of Hi, the balanced equation is 2Hi give rise to H2 and I2. Hence the molecularity is 2 and the reaction is called bimolecular. Reaction between NO and O2, the balanced equation is, hence the molecularity is 3 and the reaction is called termolecular. In case of complex reaction involving a number of ion, atom or molecule of reactant in the balanced equation, usually more than 3, the chance for all the atom, ion or molecule of the reactant to come together and collide are rare. Hence, in such case, the reactions are supposed to take place in a number of steps. The slowest step is the rate determining step. The number of atom, ion or molecule taking place in the slowest step, the rate determining step, is called the molecularity of the reaction. Thus, it is observed obviously that the molecularity of a reaction must always be a whole number, whereas the order of a reaction may be fractional. However, in most of the reactions, the molecularity of the reaction is found to be same as the order. Hence, the two are used without any distinction. The example discussed in the next section will make this point more clear. H2O2 plus H positive plus Br negative give rise to HOBr plus H2O. HOBr plus H positive plus Br negative give rise to H2O plus Br2. Reduction of nitric oxide with hydrogen. The reaction is the rate law equation is found to be. This suggests that the reaction is of the third order and the rate determining step involve 2 molecules of NO and 1 molecule of H2. Thus, the following mechanism has been proposed. Distinction between order and molecularity of a reaction. Order of reaction. It is the sum of the concentration term on which the rate of reaction actually depends, or it is the sum of the exponent of the concentration in the rate law equation. It need not to be a whole number. It can be fractional as well as zero. It can be determined experimentally only and cannot be calculated. It is for the overall reaction and no separate steps are written to obtain it. Even the order of a simple reaction may not be equal to the number of molecules of the reactant as seen from the balanced equation. Molecularity of reaction. In simple reaction, it is equal to the number of molecules of the reactant as represented in the balanced equation. In complex reaction, it is the number of molecules involved in the slowest step. It is always a whole number. It can be calculated by simple adding the molecule of the slowest step. The overall molecularity of a complex reaction has no significance. It is only the slowest step whose molecularity has significance for the overall reaction. For simple reactions, the molecularity can usually be obtained from the stoichiometry of the equation. Method for the determination of the order of a reaction. The method commonly employed for the determination of the order of a reaction are briefly described below. By using integrated rate equation. In this method, the initial concentration of the reactant and the concentration of any one of the reactant or product at different instant of time are determined experimentally. Then either of the following two methods may be employed. Substitution method. The appropriate value of A and X are substituted into the integrated form of the rate equation for the first order, second order, third order, one by one. The rate equation, which gives the constant value of K, determines the order of the reaction. Graphical method. As already derived, the integrated expression for the rate constant for reaction of different order are: for zero order, K is equal to 1 by T, A naught minus A is equal to 1 upon T, C naught minus Ct. For first order, K is equal to 2.303 upon T logarithm C naught minus logarithm Ct. For second order, K is equal to 1 by T, 1 by Ct minus 1 by C naught. For third order, K is equal to 1 upon 2T, 1 upon Ct square minus 1 upon C naught square. Hence, if the plot of concentration Ct against time is a straight line, the reaction is of zero order. If the plot of logarithm A minus x or logarithm Ct against time is a straight line, the reaction is of first order. If the plot of 1 upon A minus x or 1 upon Ct against time is a straight line, the reaction is of second order. If the plot of 1 upon A minus x whole square or 1 upon Ct square against time is a straight line, the reaction is of third order. By using differential rate equation. This method is based upon the fact that the rate of a reaction of the nth order is proportional to the nth power of its concentration, where K is the rate constant for the reaction and C is the concentration at the instant of time t when the rate is R. Hence, for two different concentrations, R1 is equal to K C1 raised to the power n, R2 is equal to K C2 raised to the power n, R1 upon R2 is equal to C1 upon C2 raised to the power n, or logarithm R1 upon R2 is equal to n logarithm C1 upon C2. N is equal to logarithm R1 minus logarithm R2 upon logarithm C1 minus logarithm C2. Thus, to calculate the value of order n, we require to know the value of the rates R1 and R2, or at two different concentrations C1 and C2 respectively. These may be found by either of the following two methods. The change in concentration is an appreciable interval of time, may be measured. The value delta C upon delta T may then be assumed to be equal to dC upon dt. At the mean value of C in the interval considered, two different intervals may be considered during the course of reaction, and the value of dC1 upon dt and dC2 upon dt. As already discussed in section 5.4, the concentration of a reactant may be plotted against time, and the rate at any concentration may be found from the slope of the tangent at that point. Obviously, this is a more accurate method than the first. Fractional change method. It has already been discussed that the time taken for a definite fraction of reaction to be completed is directly proportional to the initial concentration for reaction of zero order, independent of the initial concentration for the zero first order, inversely proportional to the initial concentration of the reactant of the second order, inversely proportional to the square of the initial concentration of the reactant of the third order. In general, we say that T inversely proportional to A raised to the power n minus 1, where n is the order of reaction. The time taken for half of the reaction to be completed is called half-life period and is represented by T half. For two different initial concentration, we may write T half 1 is inversely proportional to A1 raised to the power n minus 1, and T half 2 inversely proportional to A2 raised to the power n minus 1. Dividing one equation by the other, we get, take logarithm of both the side, we get logarithm T half 1 minus logarithm T half 2 is equal to n minus 1 bracket logarithm A2 minus logarithm A1. Ostwald's isolation method. This method can be used for finding the order of those reactions which involve two or more reactants. The method is based upon the fact that the order of a reaction does not depend upon the concentration of those reactants which are taken in excess. Turn by turn, all reactants except one are taken in excess. The order thus observed is with respect to the reactant that has been isolated from the others. The total or the overall order of the reaction is the sum of the order found with respect to the different reactant one by isolation. For example, suppose a reaction involves three reactants A, B and C. In the first case, B and C are taken in excess so that A is isolated. The order thus observed is the order with respect to A. Similarly, by taking A and C in excess, the order with respect to B can be found. And by taking A and B in excess, the order with respect to C can be found. Suppose the order with respect to A, B and C are found to be alpha, beta and gamma, then the overall order of the reaction is alpha plus beta plus gamma. Alternatively, keeping the concentration of all the other reactant constant, the concentration of one of the reactant is changed turn by turn, and the effect on the rate of reaction is studied. In this way, the order with respect to each reactant can be found, and hence the overall order of the reaction can be determined. Effect of temperature on the rate of reaction. Arrhenius equation. The effect of temperature on the rate of a reaction has already been discussed qualitatively in section 5.1, and the various terms involved like threshold energy, activation energy, energy barrier, activated complex, etc. have also been described therein. Quantitatively, the effect of temperature on the rate of a reaction and hence on the rate constant K was proposed by Arrhenius. The equation called Arrhenius equation is usually written in the form K is equal to A e raised to the power minus EA upon RT, where A is constant called frequency factor because it gives the frequency of collision of the reacting molecule. EA is called energy of activation, R is gas constant, and T is the absolute temperature. The pre-exponential factor e raised to the power minus EA upon RT gives the fraction of molecule having energy equal or greater than activation energy EA. The energy of activation is an important quantity as it is characteristics of the reaction. Using the above equation, its value can be calculated as follow. Taking logarithm of both sides of equation 1, we get if the value of rate constant at temperature T1 and T2 and are K1 and K2 respectively, then we have anti-logarithm K1 is equal to anti-logarithm A minus EA upon RT1 and anti-logarithm K2 is equal to anti-logarithm A minus EA upon RT2. Subtracting equation 3 from equation 4, we get anti-logarithm K2 upon K1 is equal to EA upon 2.303 R bracket T2 minus T1 upon T1 T2. Thus, knowing the value of the rate constant K1 and K2 at two different temperatures T1 and T2, the value of EA can be calculated. Alternatively, knowing the rate constant at any one temperature, its value at another temperature can be calculated, providing the value of EA is known for that reaction. To test the validity of Arrhenius equation, let us reconsider equation 2. It may be written as anti-logarithm of K is equal to minus EA upon RT plus anti-logarithm A, or logarithm K is equal to EA upon 2.303 RT plus log A. This equation is of the form y is equal to mx plus c, the equation of a straight line. Thus, if a plot of log k versus 1 upon t is a straight line, the validity of the equation is confirmed. This is actually found to be so as shown for a typical plot. Further, from reaction 6, obviously we will have slope of the line is equal to minus e upon 2.303 r. Thus, measuring the slope of the line, the value of EA can be calculated.